Hello everyone. In this chapter of our short course series, we are revisiting the famous calculus. Calculus is, of course, a huge subject, a huge research and study field. So, of course, we won't be covering all parts, but we'll be touching upon most important parts. In the first part of this chapter, we have seen the limit and limit theory and its applications with quite a few examples. Now, in this presentation, we will see derivatives and integrals, fundamental operations within the calculus. In the first half of this presentation, we will give the definition of derivatives or derivation operation, or with its more common name, differentiation operation. We will give definitions, meanings, and visual representations, as well as some examples. And in the second half of this presentation, we will be visiting integrals. We will also give the definitions, meanings, some practical aspects, some visual graph representations, as well as a few examples. This presentation may take too long because the topics are quite long and there are plenty of slides. So if I feel like it will be going very long, then I may stop at some point and divide the video by 2. So it will also be an opportunity for you to give a break and continue the rest of the presentation later. Let's start with the first half, differential calculus. The two basic forms of calculus are differential calculus and integral calculus, as we already mentioned. So the first half of the course will be dedicated to the former. Let's define differentiation and the derivative terms in a concise way. The study of calculus usually begins with the basic definition of a derivative. A derivative is obtained through the process of differentiation, and the study of all forms of differentiation is collectively referred to as differential calculus. If we begin with a function and determine its derivative, we arrive at a new function called the first derivative of that original given function. If we differentiate the first derivative, we arrive at a new function called the second derivative, and so on. So differentiation is, although these terms are used interchangeably, differentiation is the name of the process in a more generic approach, but the derivative is the operation itself. So, but again, you will see that in many places these terms are used interchangeably. And after second derivative, we will make another differentiation and arrive at the third derivative. So this will continue depending on the given function. From a geometrical point of view, the derivative of a function is the slope of that function at a given point. So here you see a function y equals to f of x, and there is a virtual line representing parts of that function, and at a given point we can calculate the slope of that function, but for another point we would get another slope for that function. It doesn't have to be like that always, because if we have a straight line, then we will get that slope. We will get that slope the same at every single point of that straight line. But for many of the functions, especially for higher degree functions, the slope would change depending on the given point. Derivative operation or derivative of a function can be represented by various ways. So dy on the x is one representation. It means that derivative of y with respect to the variable x. Or it could be f prime of x, or it could be df of x on dx. So all these representations are basically the same derivative operation. And using one of these symbolic definitions, representations, we can give the definition of derivative. And dy on dx, derivative of y with respect to x, equals to limit of delta y over delta x, where delta x approaches to 0. And the symbol delta here represents the change in these variables and the given function. So what we care about most here in derivatives is the changing rate of a given variable or a function. Here in this figure, we see a continuous function, but it's a piecewise linear function. So it's not like a single part or can be represented as a single polynomial, etc. It more looks like merging several functions and getting a new function, but at least it is still continuous. In this example, we see another piecewise linear function, but it has some discontinuities. So it's not a continuous function. It has some finite discontinuities, as you see, where x is equal to x1. There is some holes, some gaps. There is some discontinuities. It's the same for x equals to x2 and x equals to x3. So while we have seen these previous examples, these piecewise linear functions, one being continuous and one has some finite discontinuities. Because we want to evaluate the slope. Remember that derivatives is all about the slopes of a function at a given point. So when we are calculating the derivative of this function or a similar function, we will be dealing with the slopes. We will find the slopes by getting the derivative. So as you see here, we have different pieces. Even though the function is continuous, we have different pieces merged together, and all these pieces, or let's say some of these pieces, have different slopes. The angle between each piece and the x-axis does not have to be same. Here we have different pieces with different angles. And here, even though the discontinuities, we have different pieces with different angles. The first one, for example, between x1 and x2 has no slope at all, but the next one has some slope. So it will hint us that the derivative of that function would be different in different pieces. And let's remind, how do we calculate the slope? We have to find the vertical length of that line segment, vertical distance from the x-axis, and the horizontal distance from the y-axis. Then we will calculate the slope using the tangent, one of the trigonometric functions. Slope of a piecewise linear segment would be dy on dx, and which is equal to y2 minus y1 on x2 minus x1. So this would be the tangent of this linear segment. If we accept this linear segment as a right triangle, then the tangent would give the slope. And it is the derivative of y with respect to the variable x. Here the example question asks us to plot the first derivative of the function shown below. So it's pretty much similar to the first example. Here we have 1, 2, 3, 4 line segments with different slopes. So we will plot the function, derivative of the function. And here in this next slide we have the original function itself on top, on figure A. At the bottom, on figure B, we have the derivative. For the first line segment, the result is a straight line with value of y equals to 3. Because dy on dx, and which is also f prime x, the derivative of fx at that range is 3. It's only 3, so it's not changing. And the answer lies in this this slope formula here. It says the slope is calculated as y2 minus y1 over x2 minus x2. Let's look at what is y2 and y1 and x2 and x1. So here, for this very first line segment, the y value, the result of fx, is 12, and y1 value is 0. So y2 minus y1 would be 12. And here in this x-axis, for this very first line segment, x2 is 4 and x1 is 0. So the denominator of this formula would be 4 minus 0, which is 4. So what we should do is divide 12 by 4, which will be 3. And all the other line segments are found using the same method. You can stop the video here and verify the results. Now we will follow the development steps of a simple derivative of a non-trivial function. Sorry, I mean a trivial function, which could easily be y equals to x squared. It's a basic polynomial with a degree of 2. And if we add a little change to that function y, it could be y plus delta y, a little change, and this could be x plus delta x squared, because of the relation between x and y. And if we continue the multiplication, y plus delta y would be x squared plus 2x delta x plus delta x squared. We can still continue from here, and if we leave delta y alone on one hand of the equation, we will get delta y equals to 2x delta x plus delta x squared. How did we do that? Because we already know that here from the original question, y equals to x squared. So whenever we see y and x squared on opposite sides of the equation, we can make a simplification. Here, this y and x squared would be equal, so we can omit them from the equation. And what we get here is delta y over delta x. If we divide delta x both sides with delta x, we will get delta y over delta x equals to 2x plus delta x. And from here, we can calculate the limit of this function representation, and we will get dy on dx limit delta y on delta x, where delta x approaches to 0, is 2x. It was quite straightforward because delta x approached to 0, so eventually at some point it will reach 0, or it will be very close to the number 0. So if we add something very close to 0 to a number, we will basically get that number itself. So this is why we get 2x as a result. So we could just prove that derivative operation using the limits. When taking derivatives, there is a rule called the chain rule, and sometimes it could be quite handy when solving problems. Let's assume that y equals to f of u and u equals to u of x. So both are functions. And in this case, dy on dx, the derivative of y with respect to x, would be dfu over du times du over dx. We just wrote fu instead of y here, so we just make substitution, a simple algebraic substitution here. And in the end, we get f prime u, the derivative of f, times du on dx, so derivative of u with respect to x, where f prime u equals to dfu over du. Whenever a function is fed with another function as a variable, we will be using this chain rule a lot. This example asks us to approximate the derivative of y equals to x squared at the point x equals to 1 by forming small changes. So it asks us something like the limit approach, but from a numerical point of view. If y equals to x squared, then y1 would be 1 squared, which is 1. And let's move a little step forward and add 0.01 to x. And then we will get y of 1.01, and this would be 1.01 squared, and it must be 1.0201. So it's a very small number, but still it will be useful for us in later steps. In this case, delta y, the change of the value of y when we make a little change in x, would be 1.0201 minus the original value of x, which is 1. So the difference would be 0.0201. So dy dx could be delta y on delta x, which is equal to 0.0201, the difference we calculated on the previous step, over 0.01, and this should be 2.01. So here, in this case, we get the derivative very close to 2. And if we use even smaller steps, smaller changes like 0.0001, then this value would be really much closer to 2. And this indicates a limit on 2, and the result of the derivative where x equals to 1 would also be 2. So sometimes we can also use numerical approach. In the next example, the derivative of sinus u with respect to u is given below. It is d sinus u du equals to cosinus u, which is really correct. And the question asks us to use the chain rule to find the derivative with respect to x of the function y, which is defined as 4 times sinus x squared. So we know what is the derivative of sinus function, sinus u, with respect to u, and the question asks us the derivative of 4 times sinus x squared with respect to x. So here u and x squared are equivalent. Let's start solving. U is equal to x squared, and du on dx, du dx would be derivative of x squared, which is 2x, and dy dx would be f prime u du dx, and this could be dy du times du dx, and here we have du on both numerator and denominator parts of this division. And the result would be 4 times cosinus u times 2x, which could be represented as 8 times x times cosinus x squared. Now you see a very handy table showing derivatives of some well-known and most popular functions. Here fx is the given function, f prime x is the derivative of that function, a is a real number, u and v are other functions as well, and n is also a real number. So what you should remember here is u and v are functions, a and n are numbers, not functions. So a times fx, derivative of a times fx would be simply a times f prime x. It doesn't change the derivative of f function. You can just multiply a function, and if you take the derivative of that multiplied version of the function, the derivative of the function would also be multiplied with the same coefficient. And let f of x would be sum of two other functions like u of x plus v of x. In this case, we can also add the derivatives of these functions and find the derivative of the original function. So derivative of u of x plus v of x would be derivative of u of x plus derivative of v of x. So shortly, u prime of x plus v prime of x. Derivative of f of u, where u is another function, can also be calculated with respect to x. So derivative of f of u would be f prime u times du dx, which is equal to dfu du times du dx. So even though u is a function, we can still take the derivative of f with respect to x. And there is a short way of doing this. Derivative of any constant number is 0, period. So this is the one of the most basic rules. Derivative of constants are 0. Derivative of x to the power of n, where n is not equal to 0, would be n times x to the power of n minus 1. This is also another fundamental formula. Likewise, we can calculate the power of u, where u is a function of x. So derivative of u to the power of n, where n is not equal to 0, could be n times u to the power of n minus 1 times du dx. Derivative of multiplication of functions u and v could be u times dv dx plus v times du dx. And we can also calculate derivative of division of functions u on v. The result would be v times du dx, which means that derivative of u with respect to x. So v times du dx minus u times dv dx over v square in the denominator part. And we have a quite interesting derivative here in the last row. It's derivative of e to the power of u. And e is a very special number, so it creates some magic. Derivative of e to the power of u equals to e to the power of u. Again, it's the same. It's not u minus 1. It's e to the power of u times du dx, which is derivative of u with respect to x. We have several more derivatives, but these are also quite important, so I will not just basically skip these ones. You do not have to memorize all of them, so it's the 21st century. You can always find what are these online using Google or other websites like Wolfram Alpha, etc. You can always find the solutions, or you can use your calculator for some of the questions. But if you remember, you will save time. So that's the rule. You can find them from books, websites, etc. But as long as you remember, you will save time. And time is quite important these days. So if you can try to memorize at least a few of them. Okay, let's continue. A is a constant, so a to the power of u, where a is a constant and u is a function of x, could be defined as ln a times a to the u times du dx, where ln is the natural logarithm. By the way, derivative of ln u can be expressed as 1 over u times du dx, so it's a very simple one. Derivative of ln u is 1 over u times du dx. And logarithm of u with base a could be written as logarithm of e with base a times 1 over u times du dx, where du dx is derivative of u with respect to x. Derivative of sinus u is cosinus u times du dx. So if u is only x, then what you will get is cosinus u or cosinus x. So sinus x would give cosinus x. because derivative of x with respect to x could be 1, and cosinus x times 1 should be cosinus x. Likewise, derivative of cosinus u is minus sinus u times du dx. Derivative of tangent u is secant square u times du dx, and arcsinus u, derivative of arcsinus u is 1 over square root 1 minus u squared times du dx, where arcsinus u is defined between minus pi over 2 and positive pi over 2. For arccosinus u, it's the negative of the result of arcsinus u, but the ranges are quite different. The range is between 0 degrees and 0 radians and pi radians. For arctangent u, the derivative is 1 over 1 plus u squared times du dx, where arctangent u is defined between minus pi over 2 and positive pi over 2. We have another example here. It says determine dy dx for the function shown below, and the function is y equals to x squared times sinus x. Here the derivative dy dx is u times dv dx plus v times du dx. If you ever ask how did we proceed until here, notice that y is actually multiplication of two different functions of x. So the function 1 is x squared and the function 2 is sinus x. And here in the previous slides in the table we have multiplication of two functions uv. It is defined as u times dv dx plus v times du dx. So what we are doing here is setting u as x squared and setting v as sinus x and applying the formula here. And we will now in the next step substitute v and u with x squared and sinus x in the corresponding places, and we will get x squared times d sinus x dx plus sinus x times dx squared dx. And if we execute these derivatives using using the table, if you did not memorize the results, we will get x squared times cosinus x plus sinus x times 2x. And the eventual result will be x squared cosinus x plus 2x sinus x. So it's a little bit tricky, but not very hard at all. Another example is coming. Says determine dy dx, so derivative of y with respect to x for the function shown below, and the function is y equals to sinus x over x. For this question, what should we do is using the division formula given in the tables here. As you see, we have u over v defined as v times du dx minus u times dv dx over v squared. Looks kind of complicated, but not that much. So if we apply this formula to this question, we will get the result pretty straightforward. So dy dx equals to v times du dx minus u times dv dx over v squared, exactly what is written in the table. Now we do the substitution. Here u is sinus x and x is v, and the function becomes x times d sinus x dx minus sinus x dx dx over x squared, and the result would be x times cosinus x minus sinus x over x squared. Another one is coming, says determine dy dx for the function shown below. The function is y equals to e to the power of minus x squared over 2. And here for the substitution, we set u as minus x squared over 2, because let's look at the table again. We have, not this one, the previous one, yeah, here in the bottom row, and the last row, we have e to the power of u defined as e to the power of u again times du dx. So what is written in the power exponent should be called u, and we should then continue the derivative. So the power exponent here is minus x squared over 2, and it is defined as u. And now if we apply the formula, we will get d minus x squared over 2 dx, which is 2x times minus 1 over 2, which is minus x. This is the derivative of u with respect to x, not the derivative of y itself. And from this point, we will get the derivative of y, which is e to the power of minus x squared over 2 times minus x, which is minus x times e to the power of minus x squared over 2. It takes time, but if you have the table, or if you can memorize the things, how the things is going on, then it will be easier. Let's revisit the higher order derivatives. So if y equals to f of x, then dy dx, the derivative of y with respect to x, could be f prime x, which is df of x dx. This is the first derivative. And the second derivative would be d squared y dx squared, which is also shown as f double prime x, which is equal to d squared f of x over dx squared, which is d dy dx dx. So when reading this stuff, it doesn't make sense all the time, but if you follow the slides, then you will get a better understanding. And in the last row, we have d cube y dx cube, which is the third derivative of this given function. So it's not actually cube, but for sake of simplicity, it's common to read these like that, but it's actually the third derivative, so it's not cube of d. And it's defined as follows. It's also common that we use triple primes for the third derivative. But if it is bigger than 3, for 4 and 5, we do not use primes, apostrophes. We use the number, the order of the derivative within a small parenthesis on the superscript. Here this example says determine the second derivative with respect to x of the function below, where the function is y equals to 5 times sinus 4x. So let's find out the first derivative. It should be 5 times cosinus 4x times d 4x dx, and the result would be 20 cosinus 4x. So here, if we take the derivative of this result, we will find the second derivative of the original function. So d squared y dx squared could be 20 times minus sinus 4x. Remember the derivative of cosinus, it should be minus. 20 times minus sinus 4x times d 4x dx, and it is equal to minus 80 sinus 4x. You can continue taking derivatives of these trigonometric functions forever. Derivatives have a very good, very handy use case. It is finding maxima and minima, so maximum and minimum points of a given function. In order to find these points, we use derivatives. First, we determine the derivative of the function. So then we set the derivative to 0. We make an equation which is equal to 0 using that derivative and solve for values that satisfy the equation. And then we determine the second derivative of this equation. And if the second derivative is greater than 0, that given point is the point we find from the equation is a minimum. Otherwise, if the second derivative is smaller than 0, then the point is a maximum. Because remember that derivatives are all about the slopes. So if we find that the function becomes smaller, the values of a function, the results of a function become smaller and smaller at a certain point, then that point should be a maximum, at least locally. Displacement, velocity, and acceleration are not directly related to electrical engineering or computer science, but these are very fundamental topics, so it's always nice to take a look at. If we say that displacement is y, then the velocity velocity v is dy dt. So in other words, velocity is derivative of displacement with respect to time, because displacement changes by time. If we are moving with a constant speed or a varying speed, doesn't matter. If we have some speed and if we are moving, our cumulative displacement will change over time. And this formula here, this little formula, exactly says that v equals to dy dt, says our displacement changes when time changes, and the amount of this change is velocity. And acceleration a is the change of velocity with respect to time, so it's dv dt, and it's also written as the second derivative of displacement with respect to time. So if you know displacement, then you can get velocity. If you also have some idea about the time, you can get velocity from displacement, and you can get acceleration from velocity. So if you know the displacement, you can get velocity and acceleration with the given time or time span. We have another example regarding local maxima or minima of function. Says determine local maxima or minima of the function below, and the function is y equals to f of x equals to x cubed minus 6 squared plus 9x plus 2, and dy dx, the derivative becomes 3 times x squared minus 12x plus 9. Here, remember the second step. The first step is finding the derivative, and the second step is setting the derivative to 0 and solving the values. So what we should do is setting 3 times x squared minus 12x plus 9 to 0 and finding the satisfying values, which are x equals to 1 and x equals to 3. If you try these values, you will get that 0, the equation is satisfied. And at this point, we already find the points. So let's look at the next step. It says determine the second derivative. Here we should take the second derivative, which is 6x minus 12. And what we should do here is trying the points and seeing if the result is positive or negative. For x equals to 1, f double prime of 1 makes minus 6, so it is negative. Then the point is a maximum, and y max, the maximum point of function y, is 6. And this is the result of the original function when we apply the point we find. And for x equals to 3, f double prime of 3 would be 6. And this point, since this result is positive, this point is a minimum. And y minimum is 2. So without drawing the graphs of a function, we can find maximum and minimum points. We are done for the first half, for the derivative part, but it's already past 45 minutes, which is quite long for a short course time span. So it will be better if we stop here, take a break, and continue the integral calculus part, the second half, in a separate video. So I will finish the video here, and I will start the integral part of this session in a second video.